Hi everyone, my name is Brendan Lin and today I'll be walking you through Lab 2. In this lab, we explored Newton's second law and the momentum principle and looked at how they apply to analyzing motion and forces in real-world scenarios. Newton's second law, F equals ma, gives us a snapshot of motion. It tells us what's happening in a single instant. For example, if I push a cart, the harder I push, the faster it accelerates. The momentum principle F equals dp over dt is more like a before and after video. It looks at how momentum changes over time, which makes it especially useful for quick, messy events like collisions, or for systems where mass is changing like rockets burning fuel. Both ideas are powerful, but they're used in slightly different ways depending on the situation. In here, we track the motion of a 500-gram mass rolling on a table using tracker software to analyze a video recording. To compare this to real-world motion, we built a computational model in GlowScript to simulate how the mass should move in a perfect frictionless environment. Finally, we graphed both the observed and predicted data to see how they compared. We tracked the motion of a 500-gram mass rolling on a table using tracker software to analyze a video recording. To compare this real-world motion, we built a computational model in GlowScript to simulate how the mass should move in a perfect frictionless environment. And finally, we graphed both the observed and predicted data to see how they compared. To make my computational model match the real world, I changed a few settings. I set the ball's mass on the given GlowScript to 0.5 kilograms and gave it a starting speed of 0.278 meters per second. I also told the program to only run the simulation for 2.27 seconds and to update the ball's position every 0.03 seconds to line up with the video frames. The model then used the basic physics formulas for position and velocity to figure out where the ball would go. The most important assumption I made was that after the initial push, there were no more forces acting on the ball horizontally. That's why I set the acceleration to 0, and the program just shows the ball coasting along at a steady speed. These are the graphs for no drag. For the gravity plus drag, I also changed a few settings. I left the ball's mass at 0.5 kilograms and I changed the speed to 0.278 meters per second. I kept the amount of time running the same, and I also told it to update the ball's position every 0.03 seconds, same as the first time. And I also made the assumption that there were no more forces acting on the ball horizontally, so I once again set the acceleration to 0. So the program just shows that the ball's coasting along at a steady speed. These are the graphs. And this was my tracker data. The first graph shows the recorded data from tracker. The second one shows the GlowScript data with drag, and the third one shows the GlowScript data without drag. So these are all of my data on one graph. And for the discussion of the graph, as we can see, the observed graph follows a line slightly above the predicted graph. Both predicted graphs remain consistently below the observed data. The drag force equation we use here was F drag equals negative b times v squared times v hat. There are several possible sources of errors that could explain this difference. First, the observed data doesn't match either predicted one, which suggests some inaccuracy in our setup, and one factor could be the camera distortion, such as lens warping. Another source might be tracker's built-in velocity table, which may not fully capture the true velocity, and it's also likely that the actual velocity was higher than the values we used for our prediction. Finally, the drag coefficient we input may have been too large compared to the drag acting on paper. So for my what-if question, first, terminal velocity happens when the net force is 0. That would show up as a flat horizontal line on the velocity versus time graph. None of my models reach this, but we could capture it by running the experiment for a bit longer or launching the object downward with a higher speed. Second, imagine if we had thrown the object straight up with the same starting speed. It would take longer to hit the ground since all velocity would be vertical instead of split between vertical and horizontal components. The forces gravity and drag stay the same, but the motion plays out differently. And for the what does this mean? The takeaway here is that while models like Newton's second law and the momentum principle are powerful, the accuracy of our predictions depends on experimental setup, measurements, precision, and the assumptions we make. By comparing models with real data, we get a better sense of what theory matches reality and where it needs adjusting. Thank you for listening to my presentation.